All right, so we talked a little bit about partial fractions and why they're important. Now we just got to figure out some basic ways on how to do it. So partial fractions basically says that if I can have some kind of whatever, so I've got some kind of blah, 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 some kind of function. See, I hate to use function notation because then that scares you off. So let's say that I've got some kind of function here, and I have some kind of function-y function that, you know, I don't know, factors here on the bottom, blah of x, that it can be rewritten as a combination of things that have versions of this on it. But it's not quite that easy. Okay, so we're going to talk about why it's not quite that easy, and then do it. So actually, we'll just go ahead and do that. You shouldn't use things that say blah on your paper because your teachers get irritated. So here's kind of a simple, not really simple. We just pretend it's simple, so it's not scary. Kind of a straightforward method, or what you would normally encounter doing partial fraction decomposition. Okay, so say you've got something like linear factors on the bottom. So let's look at it that way. So let's look at some cases. So case 1, let's say we have unique linear factors. So by that I mean stuff that's in the denominator, or whatever you're trying to partially fractal, the fraction-y stuff. Denominator, okay. So whatever you're trying to do into partial fractions, say the denominator has unique linear factors. So say I have something, and I'm assuming you can factor before you do this, because if you can't, it's just not going to happen. But say I've got, say 3x plus 2, and 5x minus 1, and 2x. That's still linear. What I don't have, so this doesn't have no x squared, x cubed, no natural logs, no exponents, no trig functions. So nothing weird, just simple lines. So the line like mx plus b. So linear means mx plus b. So it fits kind of that pattern. And they're all unique, which means nothing repeats. Okay, so assuming that you have something with no repeating and it's all linear, then it's really kind of as straightforward as matching 3x plus 2 goes on 1. A little shorter. Then you've got whatever your next factor is, and then whenever your next factor is, and I could even like put a 6 out there, that would still count, and then 6, like that. Those are all linear factors. So in case you're freaking out, this is a case where like for mx plus b, b would equal 0. For mx plus b, m would equal 0. But it still counts as linear because it fits the pattern. Then you write those on the bottom, and then you just come up here on top, a, b, c, and d. And then you find those using the method that we just talked about in the intro to partial fractions. And I don't want to get involved in actually finding all of these right now because that's going to take more time. And I don't want to distract you. I just want to look at the cases first. Also, it's important to know this could be anything. It could be, you know, plus 2x plus 7 or whatever. So this doesn't have to be a 1 on the top, but we don't really care what's on the top. Stuff is on the top, and then we're just trying to partially fraction it out. So we're going to, and we'll work some more. I just want to kind of talk about all the different cases first. All right. So case 2. So case 1 is unique linear factors. 2, 3, 3. So case 2, we'll call this, what should we do? What should we do? We could say repeated linear factors. Okay, so non-unique linear factors. So say we've got stuff on the top, and on the bottom we've got, I don't know, 3x plus 5 squared, and then we've got like a 2x. Okay, now this is a little bit different. It's really not too big of a deal, but basically what you do is you repeat. Let's make this a 2x cubed just to be fun. Basically what you're going to do is however many factors you have is how many little terms you're going to have. So here I actually have 5 factors, right? I've got 2 of these, and I've got 3 of those. So I actually have 5 factors now. They're repeated, but I do have 5 of them, and I do need to take that into consideration. So what I'm going to do is I'm actually going to write 5 of these. 3, 4, and I'm going to run out of room, 5. Okay, I can do this. 3, 4, 5. Okay, so I've got my 5 factors. Now I have 3x plus 5 as one of them. Now it would be silly to write 3x plus 5 again, so I'm actually going to write 3x plus 5 squared. Got it? Okay, then for the 2x plus 3, I'll write 2x. 2x cubed, I'll write 2x. And then I'll have 2x squared. And then I'll have 2x cubed. And if I can put it together like that, then it all works out and it's beautiful. Make sense? And then I'm going to go over here and I can just fill in A, B, C, D, E. And I'm going to find those factors on my own. Now, so that's case 2. Now, before you freak out and go, well, wait a second, because couldn't 2 be factored out? So you'd have 3x plus 5 squared, and then you'd actually have 8, and then you'd have x cubed. Like, don't you have to have like a separate one like we kind of did up here? And the answer is it really doesn't matter. You can, but it's all going to come out in a wash. Like, it's going to end up canceling out, and it's going to be just beautiful. So don't freak out about constants. Freak out about linear functions. All right, so that's kind of 2 cases there. Let's see, what else can we think of? Let's try case 3. Let's talk about unique quadratic factors. So remember, a quadratic is anything that's like ax squared plus bx plus c. So anything with a squared term in it, and unique still means that there's no repeats. All right, so if we're going to have something like this, it's still the same style, it's just a teeny bit different. So say we've got something on the bottom that goes to, like say we have x squared plus 5. Now that doesn't factor, right, because that's a plus. We have x squared plus 5, and then we have 2x plus 6, and then we have 3x squared minus 3x plus 7 or something like that. And then we have stuff on top. All right? And still nothing is repeated. So, so we're good. So, actually, I'm going to run out of space. With the magic of technology. All right. So I still have 3 individual factors, right? 1, 2, and 3. Okay, so the first one is x squared plus 5. The next one is 2x plus 6. And the next one is 3x squared minus 3x plus 7. Now, the only thing you have to do different here is basically whatever you put on the top has to be 1 degree less than what you have on the bottom. So this is considered like a, I think it's a 2nd degree polynomial. And this is really getting into some more math than I meant to. So that means up here on the top, you're going to do a 1st degree polynomial, because it's 1 less. So instead of having an x squared on the bottom, on the top, you're going to go, instead of just doing a by itself, which is actually a 0th degree polynomial, it's a constant, you're going to have ax plus b. So now there's 2 different things to guess on the top. All right, then we go to the next guy, and it's 2 plus x, so we can go a little bit more basics here. This is a 1st degree polynomial, so we're just going to put a constant on the top. Now over here, we have another 2nd degree polynomial, so on the top we go dx plus e. And now it's just a case of actually solving for the, what do you call it, the constants, the unknowns. And that gets a little bit harder, but, you know, it's just algebra. It can't be that bad, right? So, so we've got that. Now, believe it or not, I'm listing separate cases, but they're all going to kind of fall into here. Case 4, lots of stuff that can repeat. So let's just say I've got something just completely ridiculous, but everything we've done is assuming that we fully factored it as much as we can possibly stand. So I've got something on top. Let's say on the bottom I have x cubed, and then I have x squared plus 5, and 5x plus 3, and then I have, I don't know, x squared plus 2, but that's squared or something like that. And then I have, let's make more. Let's do 3x minus 2. All right, so if I look here, I have 3 factors, I have 1 factor, I have 2 factors, and then I have 1. So I have, what is that, 4, 5, 6, 7. So I have 7 factors total. So that means I'm actually going to have 7 equal signs. And now you see why I don't want to do this. Well, I do want to do it. What I mean is I don't want to solve for all the constants. I just want to show you how to do it so you can solve for the constants. All right, so now I'm going to do basically the same thing that I've done before, where I'm going to look at the x. So first I have x, then I have x squared, then I have x cubed. All right, now the next thing, I have not long enough of a line. I have x squared plus 5x plus 3. And then I have 1, 2, 3 more. 1, 2, 3 more. So I only have one of those, so I only list it once. Now I have 2 x squared plus 2, so x squared plus 2 I'll list it once. Then I'll list it again. And then the last one, I only have one of those, so I list it once. Now, as I'm going across here, this is where you got to kind of pay attention. So for this x cubed, we're going to follow the rule of what goes on top based on what goes on the first one. So what I mean by that is the x, since it's a first order, I'm just going to put a constant above it. And I'm just going to put a constant above these. So whatever I do for the first guy, every time I've repeated it, I'm just going to do the same thing. So don't overthink this. It's all going to work out. Just trust me, okay? All right. And if you do it a little bit different, it will probably work out. It just might not look the same, but then they'll all simplify to the same thing, and that'll be fine too. So then I'm going to look at this one and say, okay, well, that's the second degree. So up here, I'm going to go dx plus e. Now this guy is also a second degree, so this is fx plus g, and I've got that another time, so I've got, hx plus I. So these have to match because they're paired. These have to match because there's 3 of them. That guy, just do what I need to do with it. And then over here, this one would be just a constant because the guy under him is linear. And that is basically how you're going to do partial fractions. And I don't think I've ever done this in a classroom, but if you're wondering, if you did get something that was like stuff on the top, but then you had like x to the 5th plus 3x squared plus, x plus 5 times, so something like that. So the 3x plus 1 would still have the constant in front of it, or on top of it. And then the x to the 5th plus 3x squared plus x plus 5. On the top, it would have a 4th degree polynomial. So bx to the 4th plus cx cubed plus dx squared plus e. And that's really why you never do that in the classroom, because by then you just learn how to use MATLAB and move on. But that's kind of the basic cases of partial fractions, and we can do some practice.